Hi, I'm Jane Hawkins. I'm here to talk about the mathematics of cellular automata, a book I wrote for the AMS for undergraduate series.
Awesome. Thank you so much for meeting with us today. This is very exciting. I'm going to get started with the first question, which is what inspired you to write this book?
The subject is both interesting to me, and I noticed that a lot of undergraduates like it a lot. It's visual, it's dynamical, and you can explain it in simple terms, but you can explain it precisely. So I thought I would try to write that down.
Right. Awesome. What do you hope readers will take away from your book?
Well, I'm hoping that they'll learn some dynamical systems. That is to say, it's a deep subject, but this is a good introduction to it. So I'm hoping they'll get excited about the bigger field by reading this book. Also, I hope that they just enjoy it. It's visual, it's got color in it, it's pretty simply written, but on the other hand, it has rigorous proofs in it. So if they work their way through it, they'll know how to prove theorems.
Is that how you hope this text will help students learn, with the proofs? Or is there anything else that you think will help students learn from this book?
Well, it sort of uses a lot of different approaches. It has a lot of color in it. So if you prefer color to numbers, you can just look at the colorful drawings in it, but they all mean something, they have significance. It also introduces some abstract ideas and some concrete examples. So it also has grids in the book. You can write in the book, you can color in the book. So it sort of caters to a lot of different learning styles.
I love that it has interactive elements. When I was in school and I was doing my homework or reading, it always helped when I could write in the book. I felt like I memorized the material a lot better that way.
Yeah, I designed it especially so that people could write in it and even fill in some grids. There are a few pages that say, this is an empty grid. Here's a mathematical rule. Color it, get a couple of colored pencils and color it in according to this rule and see how it looks. Some people prefer that, and there's exercises that say, prove this result. So I tried to kind of be all over the place, hopefully not too far all over the place.
Sounds great. Do you have a favorite section or chapter or problem in this book?
I think I have two favorite chapters.
Ooh, let's hear about it.
In chapter 2, you're done with the introduction and you sort of get this mini math course all at once where you do some algebra, topology, calculus, but just little snippets and kind of in this simple setting. So you get the idea of how these different fields interact, which you often don't do at a lower level. So that's one of my favorite ones because it's all the areas of math combined, but that's a math section. And then the last, well, I think it's probably chapter 7, not quite the last one, is called Stochastic Cellular Automata. And that kind of started my own interest in this specific field because it talks about virus dynamics. So that's something very real. And it talks about HIV. And then at the end, there's exercises, labs about Ebola, COVID. So that was fun too. I mean, in a biological way.
That sounds interesting, especially since the recent pandemic. I'm sure there's a lot of ways to tie that in there.
Yes, when I wrote the book and taught on this topic, there was no pandemic. I was mainly focused on HIV, but virus act the same way. There's sort of universal dynamics to virus. What's different is how the body reacts and the speed at which the virus can replicate and so on. But this sort of gets to the universal mathematical truths of how virus interact. So it was interesting that when COVID hit, I thought about the context in which you could study it.
It kind of brings a new light into the book a little bit.
Yes.
So that's awesome. Is there a particular problem or exercise in this book that you find especially interesting or challenging? And if so, can you show us how it's solved?
I think I'll mention one that I don't know how to solve because I'm hoping a reader would solve. When you study these systems, they have simple rules, but they get very complicated. Sometimes they get complicated. Sometimes they get very simple dynamics. And the classification problem is the open problem of interest. Namely, how do you know whether two of them are going to be the same? Or if you just see the math rule, which is very simple, how can you tell whether it's going to be a chaotic one or a very simple one? So I present one classification and I discuss a second one in one dimension, which is where the symbolic dynamics go in a line. And then there's a chapter where I say if you put it in two dimensions, then the classification is pretty wide open. So the classification problem, and this is universal in mathematics, when people look at systems, they want to put them in groups and say these all behave the same, these all behave, so classifying them. And there's no agreed upon classification for these at any level. So it's really an open research problem that can be understood just, from this book.
Wow. I like how you gave a problem that you don't know how to solve yet. It really speaks to how math, sometimes there is one answer and sometimes there can be multiple answers. So
yes,
awesome.
And this book presents multiple answers, and also maybe by the time you get to the end of the book, the last chapter is called Open Problems and Other Areas to Explore. By the time you get to the end of the book, hopefully you're interested in the subject, and then the last chapter gives you lots of things to think about. So
that's awesome. What sets this book apart from others in the field?
Good question. It's a field that is quite old and started before computers. So there were kind of rigorous books written before computers with no pictures. And now there's coffee table books because they make beautiful pictures. But there wasn't really a book that took the mathematics, calculus, and algebra as we understand it in our lower level undergraduate classes and put it together with the pretty pictures. So I couldn't find a book that put these together, so I decided to write it. There are a lot of research papers on this with open questions and really deep results, but those are inaccessible to many, many people, and many are inaccessible to me. So I really wanted to put this together so that an undergraduate could read it and understand it, and I couldn't find another book that did it.
Wow. And now we have one, thanks to you. Is there anything else you would like to say about this book, about yourself, anything?
So I work in dynamical systems quite generally, and I've worked in it for many decades. And this is just one facet of a really beautiful field that's really deals with any kind of system that changes over time, mathematical, physical. And this one happens to be very easy to approach with very simple rules, and calculus helps you do it. If you like the subject and you like the dynamics, it can get much more complicated with much more beautiful pictures very quickly.
Wow. Well, thank you so much for your time today.
You're welcome.